This is Lee's Ferry. I've been here many times. It's where we always load the boats when we start our Grand Canyon trips. This is my friend, Tom Vail. He started Canyon Ministries and took me on my very first trip down the canyon. No one knows the canyon better than Tom, and I was fortunate to have him as my guide on all the canyon trips I've taken. This is Dr. Andrew Snelling, and sitting next to him is Dr. John Whitmore. Both are geologists. You may recall Andrew from our last film, Is Genesis History? Remember, Andrew took me to an extinct volcano in Arizona to discuss radioisotope dating and the age of the Earth. John was Andrew's assistant on this trip. He's been a geology professor at Cedarville University for over 30 years. He has also spent a lot of time studying the Coconino sandstone layer in the Grand Canyon. The conventional paradigm says the Coconino sandstone was formed over millions of years in a desert by the wind. But John's research has clearly shown that it was formed rapidly underwater during the flood. This is a key piece of evidence for the creation model. Little did I know that the same year we released Is Genesis History in theaters, Andrew was embarking on a research project down in the canyon. He was looking for new evidence that many of the enormous layers of sediment we see all around the world were laid down during the flood. One of the things that has always fascinated creation scientists are the huge folds that can be seen in the canyon and all over the world. Andrew had a theory he wanted to test. If his theory was correct, it would be important new evidence regarding Earth history and the geological timetable. These two scientists have spent much of their lives finding evidence that supports the history of Genesis. But in all those instances, their work was never filmed. This time was different. They took a cameraman with them into the canyon to capture what they were doing. When I heard about it, I realized that this was a way to show something most people have never seen: creation scientists doing the actual work of science. How do scientists connect the history in Genesis with the world around us? How do they test their theories? And what did the flood do to create the world we live in today? Our first documentary provided an overview of creation science. But in this documentary, we're going to explore how creation science actually works, because it is important that you see for yourself how scientists do science. I'm Del Tackett. I'm excited to be your guide as we explore the rise of mountains after the flood. Although I wasn't a part of their first trip to the canyon, I met them many times on their journey. And just like the first film, I learned an incredible amount. But this time, I found myself asking questions I had never thought to ask before.
So this is John's lab?
Yeah, I've been here at Cedarville for 30 years now, and done a lot of work in this lab and a couple other labs that are next door to this one. Over here we have what's called the petrographic microscope. This is a microscope that's designed for looking at thin sections. And this is what a thin section.
The slides
Yep.
that Ray produces for you?
Yep, this is what Ray makes. These are from his lab in Calgary. And he takes a rock like this and will slice a really thin layer off of it and glue it on a glass slide and then polish it down so you can see through it.
Yeah.
And you know, if you hold it up to the light, you can see the light passes right through that. Yeah.
Oh, that's awesome.
And so that allows us to study the sand grains under the microscope. So
It's quite an art to make the thin sections.
yeah. Here's, I've got a slide on the microscope right now, and this is one of the thin sections from the Coconino sandstones. And it has what we call ooids in here, and these are dolomite ooids.
Ovoid
Yeah,
shapes.
they look like balls almost. And what happens is you get a little sand grain rolling around in the surf or rolling around on an ocean bottom. as it rolls around, just like a kid rolling a snowball. You know how a snowball gets bigger?
Yeah.
These little sand grains accumulate the dolomite around them.
So you can see the sand grain in the middle,
Yeah.
that white spot, and all the coating around it.
You know, this was amazing evidence for us. I still remember opening up my email, looking at this, and I was just amazed, because this is just incredible evidence that the coconino was made underwater. You can't make these kinds of things in a desert. I presented this at a National Geology meeting, and I had a scientist come up that knew I was a young Earth creationist and was skeptical about all the work I had done. And every geologist would look at that and know that those were ooids, except if they're in the coconino
in front of the name.
Isn't that interesting?
As soon as it was
So
coconino.
it's just, I don't want to see this.
Yeah, he just would not look at it, would not admit, would not even study them to see if they were ooids or not. And he just said, nope, those can't be ooids, those aren't ooids, and, you know, wanted to drop the subject almost immediately. I pressed him on it a little bit, but he didn't want to go any further on
So
that.
what happens when someone is captive in a paradigm,
Yeah.
they don't want to see any evidence that's contrary to that paradigm, and that's what was happening to him.
Yeah, that's one of the neat things that we do as creation scientists. We kind of have a different way of looking at things, and so we tend to collect data and look for data that probably other people miss, or probably they might have seen it, but they really don't think very deeply about it and think about the implications. And that's one of the things I think I enjoy most about a creation scientist, because there are so many discoveries out there that are just waiting for us.
We're not constrained. We're able to ask questions that they're not asking.
And so
And that's what's kind of driven you to this research now, right?
Yeah.
I mean, because the conventional paradigm would have never gone in to take samples
No, they haven't.
to look
They've
at that fold.
They've just talked about these folds and just assumed that they were formed long after the rocks were formed, and therefore there had to be mechanisms that allowed the rock to bend when it was very hard. As creation scientists, we think these layers were laid down during the flood. The folding occurred only a year later, at the end of the flood, when the mountains and plateaus were rising in the west. If that's the case, we wouldn't expect there to be evidence of the rocks changing under heat and pressure. That's what we're investigating, and why we're making thin sections to look inside the rocks. From looking at it, anyone looking at these folds, you can see immediately they're so smooth that it seemed intuitively that these had to have been formed when they were soft. But we had to go in and get the samples so we could confirm that, plus rule out any objections that might be raised. So it's all part of doing good science. Well, I've been doing research in the Grand Canyon for 27 years. Here in the Grand Canyon, you've got exposed to view virtually a whole slice through Earth history. And so that's why it's important, because it's been used at Exhibit A for millions of years and biological evolution. And that's why it's important that creationists also come to the Grand Canyon and say, no, it's Exhibit A for creation and the flood. What's the choice?
I can do either one, Andrew. Are you deep enough over there?
Over here, okay. We're coming into the Peat sandstone here, outcropping at river level. This is our target rock unit. This is our first sample. This is the same sandstone as in the Carbon Canyon Fold. It's a good spot because it's something like 5 miles from Carbon Canyon Fold. If the sediments were still soft, we wouldn't expect to find any difference with the sample here to the sample in the fold.
Shattered on me.
I'm marking where the bedding is so we can reorient it in the lab. TSS standing for Peat Sandstone Sample 1.
Let's stop for a second, though, and go back a little bit and talk about, first of all, where the rocks came from and how you got them and why and so forth, so that
we can kind of lead up to what the research is about.
Well, a lot of people ask me the question, now, why the Grand Canyon? Let's start with something basic. The reason why the Grand Canyon is a geologist's paradise is that you've got this giant slice in the earth where the canyon and exposes all these layers. It's in a desert. It's almost a showcase in the textbooks about all these different rock layers. And so the question is, when did they form? How did they form? What is their history? We now know that many of these layers that we see exposed in the walls of the Grand Canyon stretch, in some cases, right across the North American continent and beyond.
So Andrew, the layer we were looking at in Grand Canyon is the Tapeats sandstone that's down near the bottom of the Grand Canyon. We can trace that layer into the Colorado Rocky Mountains near Colorado Springs. We can trace it into the Black Hills, and we can trace that same layer up to Greenland as a continuous sheet with no breaks in it.
So that kind of an understanding of a layer that is so huge leads your thinking more to something global than just in something local.
So that tells you something not only about the scale, but we think the flood eroded away enormous sections of the pre-flood continents, then deposited that material in layers one on top of the other. It's like a stack of pancakes miles deep all over the earth.
And so when we talked about the layers, those layers are all formed as a result of sediment, right? Talk about those layers, first of all, and how they were formed, and the layers in that we wanted to look at and why we wanted to look at them.
We wanted to look at those specific layers because they're at the bottom of that huge stack. If those layers were still soft when they were folded, they can't be hundreds of millions of years old.
So imagine a sand being washed up on a beach. How does it get cemented? How does it turn from sand into sandstone? So what happens is when it's deposited, there's water in between those sand grains, but the water has chemicals dissolved in it. And so when the water dries out, those chemicals precipitate and fill in all the spaces between the sand grains and harden it, making it a cement.
We think a lot of that cement and some of the grains would have broken if the layers were hard when they were bent.
Well, after the layers were deposited, everyone agrees that the Colorado Plateau was pushed up. It was part of the mountain building event connected to the Rocky Mountains. We think this was happening at the end of the flood when major earth movements were creating new plateaus and mountain ranges. The folded layers are the result of those movements. It's like a book. Here are the various sandstone, shale, limestone.
These are all the sedimentary layers.
Sediment now exposed by the canyon, but this was pushed up. Now, what's interesting is that the eastern side of the canyon, the layers have been buckled like that. They haven't been pushed up uniformly. And so there's been folding of the layers. And that was the focus of our research, because the conventional view is that these layers were deposited over 500 million years ago. And this folding, they say, didn't occur until 70 million years ago. So there's a gap of several hundred million years. And if that, in that time frame, you'd expect the water to dry out between all the grains, the cement to harden. Now, you know as well as I do that if you try to bend that rock, what's going to happen?
Well, first of all, I can't bend that rock, but if I think about this one.
What's going to happen?
So if this, for example, let's say this then represented that plateau that you're talking about.
Yes.
And so if we were to put pressure underneath this in order to try and bend it, and if it's hardened like this, then we would say
it's going to snap.
It's going to crumble.
It's going to crumble. See, you can bend a rock like this, hard rock, like you've got there, but you've got to do it slowly with pressure and heat, and the heat and the pressure makes the rock plastic and in a sense makes it like putty, and it will bend slowly. But because of the heat and pressure, that is going to affect the mineral grains, is going to affect the cement that binds the mineral grains together. In the conventional paradigm of millions of years, you can only cause that bending if you have heat and pressure causing metamorphic changes in the rock. And those changes will show up clearly in the thin sections. And therefore, we want to look under the microscope, is there any evidence in these layers that have been bent of those metamorphic changes? And that was a a major point, because we have to be able to show that there hasn't been those changes if it all occurred very rapidly when the rock was still soft.
So that's what drew your attention to the folds and the desire then to do the study and the research at a more detailed level.
And the interesting thing is, Del, because we have a different framework of thinking to look at these issues, we're asking different questions to what the mainstream geologists are asking. They haven't taken samples and cut these thin sections to look at the grains under the microscope. But that's very basic to understand. People can't, it's hard for people to grasp, but we're going to go to the microscope scale to explain and look at the timing of the formation of mountains.
Right.
We're zoomed in on this research project on these folds, but they are part of a bigger context. What produced these folds? So, at the end of the flood, as the ocean basins were sinking and pulling the floodwaters off the continents, an oceanic plate from the Pacific Basin went under Western North America at a fairly flat angle.
And as a result, this plate caused a number of mountains and plateaus to rise up almost to the middle of the continent, which is why there are so many high plateaus and mountains in the western United States.
One enormous area that was lifted up was the Colorado Plateau. But the plateau didn't lift up evenly, and so some areas were pushed up higher than others.
Now here's what's interesting, Del. A very large fold that goes through that area, hundreds of miles long. It's the same one Andrew was referring to, and it's called the East Kaibab monocline, where mono refers to one bend or one fold. The monocline formed a dam. Water started collecting in the lower area, and so a big lake developed and eventually found a weak point in the monocline and started to flow through it. And it was that catastrophic dam burst, we believe, that carved out the Grand Canyon.
And so it's because of the carving of the canyon that we have these folds exposed to view. And these are the places that we sampled.
Let me show you on a map where we...
Oh yeah, I'd love to see that.
So this is a geological map. You can see it's been well used.
Well used. I've had this out in the Grand Canyon many times in my pack.
You know, I can tell that if you're going to be a geologist, you need to learn how to unfold and fold maps.
That's right. Yeah, you'll notice that this is a very colorful map.
Yeah.
Every color on here is a different kind of rock layer.
When we floated down the canyon and looked at the layers, these colors now represent what we were seeing.
Yep. Every color is a different layer. Mm-hmm. The Grand Canyon goes through here. It starts way up here. In fact, the very upper part is not even on the map, but it comes down through this way, wraps around down this way, goes off the map over there, and this is just the eastern part.
Yeah.
There's a whole nother western part that sits over there, and Lake Mead after that.
Is Carbon Canyon on here?
Yep. Yes, Carbon Canyon is up here. Okay, here we come down just below 60 Mile Rapids here. We took a regional sample just above the Little Colorado River, and we came down here, parked, and Carbon Canyon is up here. Okay. And here's the fault line. And the fold is right on that fault line. That's the Butte Fault, and you can see it's a north-south, and that marks the edge of that monocline.
Yeah. So this is where you took the samples?
Yes, parked the boats, walked up to the fold. Carbon Canyon is a side canyon to the main Grand Canyon, and it cuts through the folded layers in the East Kaibab monocline. So we're coming up the drainage here of Carbon Creek, and got to go left and climb up this scree slope where there's steps. And so by hiking up Carbon Canyon, we come to the place where the Tapeats sandstone is actually bent through 90 degrees in a spectacular bend without the shattering. If we look ahead, we can follow the layering, essentially horizontal. And as we get towards the end of the canyon here, you can see the layers turn up to the skyline, almost vertical. So you can see the bend in the rocks. You know, you've been there before, but you've only got a mental picture. Now you're there in front of it. You want to check your strategy. You've already thought about what your strategy is, but now you've got to look, can I trace one particular band in the rock layers through the fold?
We've put orange duct tape in places where we want to sample, and that helps us keep track of the bed, so we make sure we follow the same bed through here. On my camera I've got a GPS unit, and so when I take a photograph, if the GPS is locked in, it will tell me precisely where I took the photograph and where our sample came from.
It's getting really upfront and personal with the rocks. Take notes to record the location of the sample, the thickness of the bed, the dip and strike of the layer, if we can obtain that information. So it's a very intense, and of course you're working on a cliff face, so you've got to watch your footage.
Oh, that's a biggie.
And then we would go in and we'd take those samples in the specified way and mark the sample so we knew where was the top of the bed, because you've got to orient it. Labels the bag, put an extra card in with a sample number. It's back to basics. This is about actually taking measurements in the field, observations in the field, making notes, and then going to look at the samples under the microscope. It's very basic geology. And then you get your samples and you get out of there as quickly as possible back to a more hospitable place.
You're in Disneyland here, yeah?
Yep, absolutely.
What is this to a geologist?
This is heaven on earth.
The nice thing about geologic maps is that the geologist will often draw a line across the map, and then he'll show you what the layers, what he thinks the layers look like underneath. So you can see these lines, like here's a B right here, and all the way up there is a B primed. And you can come down here to the map, and here's the B, and all the way over there is the B primed.
Awesome.
And notice that this particular line crosses the structure that is called the East Kaibab monocline, and that's the fault and fold partly associated with the Carbon Canyon area. And so right here is where the East Kaibab monocline goes through, and you see how the rocks are nice and flat right here, and then all of a sudden there's a bend.
Yes.
And there's a lower elevation down over here than back over here.
And so what happened, what we think happened, is the rock down here in the basement is really hard, and it broke and faulted, and that's the fault right there. But the rocks on top are relatively soft. And so as the hard rock pushed the softer rock up above, instead of breaking, these rocks up here bent and folded.
It's like having a layer of wet sand, and underneath you've got a wooden block, and you push the wooden block up and the sand will drape over the...
Right. That occurred somewhere then close to the flood time.
Yeah, well, the Tapete sandstone was deposited early in the flood, and at the end of the flood, when earth movements took place to re-equilibrate, that the folding occurred then, and the sediments were still damp and soft, and therefore they could bend quite easily, and then they dried out, and we had the cementation of the grains afterwards. And then we motored down here, and all the way past Phantom Ranch, all the way around here, come around to this is the Monument Fold. This is still the Tapete sandstone. It's actually marked on the map that there's a fold there, but there's also a fault line.
There's a fault underneath, and the rock underneath pushed up and made the rocks on top fold because they were soft. We're going to be looking at this big fold or this big bend in the rock.
You can see the granite and pushed up right here and making a big fold in the tapetes. And it looks like the tapetes has been plastically right over top of this fault. It doesn't look like the fault has extended up into the tapete sandstone at all.
And I think the easiest way to sample it is to come over and go up that slope to get to it there, and then come over and get to it on the other side of that slope.
Maybe that thin bed might be the better one to get because we're in the finer grain material.
Oh, yeah, I agree.
Yeah.
I agree.
Well, why don't you and I go up with the ladder?
Okay.
Let Andrew stay down here. We'll tape everything that we can do.
The plan is to sample 2 beds. Okay, the fold comes like this and does this. Okay, that's the overall profile. So because of the screw slope, we're going to sample in here and we're going to sample in here.
Well, it's just an interesting area that we want to try to sample. So we're going to take a sample right where this bed is kind of smeared.
And this is shifted this way, but it did so without cracking the rock.
So the rocks pose some questions to us. The folds pose some questions to us. And not just to a creation scientist, but to a conventional scientist as well. But then we want to go in there and study the rocks and look at that fold and look at the rocks under the microscope and see which paradigm fits the best.
And so the argument is not about that physical evidence, it's how you interpret that physical evidence. And to interpret it, you've got to have a framework. And our view of history is that Genesis is history. The Bible is an eyewitness account given to us by the Creator who was there. And it gives us a time frame, it gives us a description of what happened during the flood. And so we can take that description and look at the geological implications, for example, and then go out and test those implications.
Good, perfect.
Okay. 7 down, 1 to go.
So in your research was then to take samples in those folds, but you also took other samples.
Yes, well, as a control, we obviously collected samples away from the folds so that we can make comparisons. That's why we took samples from where the rocks are folded, and then we took regional samples from where the rocks are flat, but all in the same layer. If all the rocks from the different locations are the same, that's a strong indicator the layers were soft when they folded, and therefore not millions of years old.
And we made it all the way down, and we did another regional sample at Doris Rapids.
Doris Rapids up in here.
And then Mat Katameeba, we looked at a fold in the Muave. But there were other samples we got in between of the Bright Angel Shale and the Muave limestone, because these are the 3 units. And off the map we went to where we helicopter out, there's a fold there.
Yeah.
You got your pick on your side, you got your loop around your neck,
Ready to go up the ladder.
and you got
Got
a
all
ladder.
my tools on me, so I don't have to come down more than once.
A ladder like that, well, because the fold that we want to look at is at the base of a cliff, but it's still quite a climb up to it. And it's a vertical face. So we brought this ladder along so that we can get up to it. This has been in the making for what, 4 years now? 4 years. We've talked about this for a long time beforehand, but the planning to make this happen has been going on for 4 years through the whole process of getting permission to do the sampling. This is significant because you can see the way it's being folded. That sort of plasticity that enables it to bend like that without shattering. You take a hard rock, it would have fractured all the way through there, and you'd see lots of evidence of that. But you don't. Sure, there's joints there, there's cracks, but they're not shatter type cracks. The whole rock would have just disintegrated with the bending motion.
You're not afraid of height, obviously.
No, I've done a lot of house painting in my years, so been on a lot of ladders. So this ladder was very stable. And glad my wife wasn't here.
So that's an overview of the project. And, you know, as we said before, the reason we wanted to do it is nobody had actually collected samples from these folds and looked at the rock under the microscope and studied them to determine the timetable for deposition, folding, and the cementation. You know, what's the order, which is critical.
I just think that this was one of the best raft trips I've been on in the Grand Canyon. I think we collected some good samples on the trip, and we'll be anxious to see what these things look like under the microscope.
Well, Andrew,
Here we are.
what do you have to say?
Well done, everyone. Fantastic trip.
When we were in Cedarville, we were looking at the maps and discussing all the research, but asked John if there was a place where we could actually go to see the forces that caused those folds, and that took us to the Uinta Mountains.
John, the vista here is unbelievable. What are we looking at here first?
So we're at the kind of the western end of the Uinta Mountains. They extend here out to the east for another 100 miles or more. And we're looking at some of the higher peaks in the Uintas, probably right around 13,000 feet here. It's beautiful, isn't it?
It is. It is phenomenal. John, can you take me back here for a second? Let's talk about how we got all of this.
Yeah, Del, I think these mountains that we're looking at actually rose at the end of the flood. So the earth was destroyed by the flood, and then as the flood ended, Psalm 104 tells us that the mountains rose up and the valleys sank down. I think these mountains that we see in western North America and all the other high and rugged mountains that we see around the world rose up at the end of Noah's flood. That's why they're so high. They were never eroded by the flood. Other mountains that rose up earlier in the flood, like the Appalachian Mountains or the Atlas Mountains, were eroded down to the smaller mountains that we see today by the floodwaters.
So during the flood, we have those massive sedimentary layers that are being laid all over, like the Tapete sandstone. You told me this covered most of North America.
Right.
Massive, massive. But they're horizontal, right?
They are.
Most all of those
Yep.
layers are horizontal. What happened then?
Well, we see some of the horizontal layers that are in these mountains towards the tops of these mountains. And these horizontal layers actually formed below sea level. So they formed during the flood, but they would have formed at depths that were
Yes.
much lower than we're 10,000 feet right now. And so they would have formed under the floodwaters. And then after the flood, they would have risen to the heights that they are now.
Was that a miraculous event, or can we see forces at play? That God, of course, was involved in that.
Sure.
But what forces would move mountains this size?
Well, we think it goes back to our idea of catastrophic plate tectonics. And so at the end of the flood, a plate was going under western North America, creating the mountains like the Rockies and the Uintas. In South America, another plate was being subducted to create the high mountains and volcanoes of the Andes. And in Asia, two different plates collided to form the enormous mountain ranges of the Himalayas. In all these instances, we think the plates had to be moving very quickly to have the energy to create such high mountains. But these mountains formed at the very end of the flood, and that's why they're still so high.
Well, I guess the point, John, I hear you making is that even after the flood is over and Noah has landed in the ark, that there are a lot of catastrophic events that are going on all over.
That's
and that is what then shapes a lot of what we see.
You know, when Noah gets off the ark, it's not the end of catastrophe. To raise mountains up like this, you're going to have big earthquakes. And as these mountains rise, they're full of this wet, unconsolidated flood sediment. That's a recipe for huge landslides. Some of the biggest landslides that we know about are here in the southern part of Utah. So don't think of the mountains rising up as we see them right here, but think of a lot more rock in between here as these mountains originally rose up.
And so that erosion would even be more profound, I guess.
Yeah, we have big storms coming into the continents, and especially if you get those storms at high elevations like this, that water has a lot of energy as it runs downhill, many thousands of feet. Also at higher elevations like this, you have the opportunity for snow to fall. And if you have large amounts of snow that falls, you get the development of glacial ice.
And that glacial ice covered a lot of the northern part of North America then, did it not?
Yeah, it covered much of the Rockies. As you know, in Colorado, there's lots of glacial valleys there. Glaciers are one of the things that can carve those deep, steep-walled valleys in various places.
Would it be safe to say then that what we see today, not just here, but all over the world, is not what Noah saw when he got off the mountain?
That's right. And so those kinds of things, those kinds of catastrophes, help shape, help sculpt the mountains that we see today. Really nice scenery up here, isn't it?
It is beautiful, but it brings to mind here as we look at this, we have a lot of slanting of these layers. What's going on there?
So you can see the red rocks and the lighter tan-colored rocks back there. You can see they're sitting in an angle. So these layers used to be flat-lying. They're deposited in a marine setting. And these are the same rock layers that you would have seen down at the Vermilion Cliffs at the eastern end of Grand Canyon in Arizona. So here we are all the way up in northern Utah, and we're still seeing the same layers. But these layers would have had to be flat over this whole area, all the way down to Arizona and all the way up, extending into Wyoming. And then if you want to think about it as a bubble kind of rising up here, that's when those layers became slanted.
So we have the layers here on our right. Do those layers then continue and go underneath
They do.
red layer?
Those go right underneath the red layers that we see out here. So there's a whole thick package of rocks that have been kind of churned up on edge right in here.
So that means all that we see on the left used to be here on the right. Is
That's
that
right.
Is that right?
Yeah, so these layers, like this red layer, the Moenkopi, used to extend up and over. So there's a lot that's been eroded away in here. And as the Uinta Mountains pushed up, these layers would have extended over top of the Uinta Mountains. And so what we see is just the remnant that's left. And so as we look off to the north, we're looking out toward the Green River Basin. And so as these mountains rose up, it kind of made a high spot that water couldn't run through initially. And we had a big lake that formed out there. And all of this is happening approximately the beginning of the Cenozoic period around the Earth.
No, wait a second. You mentioned the Cenozoic. What is that? Where does it fit into all
Well,
of this?
geologists look at the history of the Earth in about 4 different times, if you will. And it doesn't matter if you're a creationist or a old Earth geologist, we all recognize about the same 4 periods of time. We think they had different lengths of time. The two views differ from each other, but the one that's deepest is the Precambrian. And we'll actually see those in the core of the Uinta Mountains. And then on top of the Precambrian, we have the Paleozoic. Here's some of the Paleozoic rocks, and we think these would have formed earliest in the flood. And then over here, beginning with these red rocks, that's the beginning of the Mesozoic. It means middle life. So we have Paleozoic, old life, Mesozoic, middle life. And then the most recent period is the Cenozoic, which means new life. And as creation geologists, I think these Paleozoic and Mesozoic rocks would have formed during the flood year, so we have about a year's worth of time to form all that rock, and much of that we can see right in here. But then after the flood, as this erosion is happening, where is the sediment going? These mountains get lifted up, and then the eroded sediment is going into the big lakes that are forming out there. We often talk about a lot of these sedimentary layers being made during the flood. I think there's a lot of sedimentary layers that are going to be made after the flood as well. So we can piece together a whole series of events. So we know that these Paleozoic layers had to be made first, then the Mesozoic layers had to be made, the uplift happens, and then after the uplift, we get those lake sediments out there being laid down.
Are those lake sediments then laid down fairly close to the end of the flood, or?
I think they're laid down after the flood was over. So there's a lot of good reasons why we picture the Cenozoic as the end of the flood. And we see all these mountains rising up in the earliest part of the Cenozoic. And so if you have mountains rising back up and not getting eroded down by floodwaters, that's a hint geologically that the flood's over.
John, if all of those forces are lifting up the mountains at a time where all of those layers are still soft, then we wouldn't expect to see them crumble and break. Would we see them fold? Is that what we saw in the canyon?
That's right. So we're going to drive just a little ways from here into the core of the Uinta Mountains, and we'll see one of the limestones that's bent and deformed as this uplift took place. And that tells us that these rocks were moving around while the stuff was still soft, just shortly after it was laid down.
John, I have to admit, this is pretty impressive.
So we're looking at the brown rock here, which is the core of the Uinta Mountains. And we're looking at the tan rock up there, which is the Madison limestone. It's the same limestone that we see in Grand Canyon that we call the red wall limestone there.
Okay.
The same kind of thing is happening here that happened in Carbon Canyon at the same time.
So the folding that we saw in Carbon Canyon, which doesn't seem to be nearly as massive as this, but it was the same kind of principle, right?
Yeah. So this entire area is getting lifted up. And especially here in the mountain ranges, as it gets lifted up, some of the Precambrian rocks are going to break. But they have soft sediments that are sitting on top of them. And so as the mountains lift up, the soft Paleozoic sediments get deformed, and that's that big bend that we're seeing in the rocks.
And it just folds. It's apparent to me when I'm looking at it that this was soft when all of that happened. Even in the vertical side here, we see some bending and folding.
Right.
John, also the thing that strikes me, we saw this layer in the Grand Canyon. I don't know how far away that is. It's a long ways away.
All the way across the state of Utah.
Right. But there are mountains in between there. And you couldn't get those nice flat layers if those mountains were there. So it's obvious the layers were laid down, the mountains were then pushed up, and because they were soft, then they folded instead of broke and were brittle like we see underneath.
Yeah, so that's correct, Joel. All these layers in the Paleozoic and the Mesozoic rocks that we're talking about here, these had to be laid down before these mountains are pushed up, because those are the layers that are deformed by the mountains rising.
Yeah. You see these all over the earth, do you not?
Yeah, you do. You see some other big folds like this in places like the Alps, the Appalachian Mountains, and things like that. Again, it's the same argument that these rocks are bending because they're soft. They haven't hardened yet. The hardening takes place after the bending. You know, one of the things that we want to help people understand is how the Earth got its shape. Geologists like to use a word called geomorphology. And as a flood geologist, I think a lot of that shaping actually took place after the flood was over.
Well, we've talked a lot about the deformation of those layers, the soft bending, and so forth, but this is something different. John, it seems to me that we're in the middle of a layer. What is this?
This side used to connect to that side and everything in between. So there's a lot of rock that's been removed in here.
Yeah.
So let's start with where the rock layer itself came from. I think this layer was made during Noah's flood. I've studied this rock layer in some detail down in Arizona, the Coconino Sandstone, called the Weber up here. The layer extends all the way from California up to the Dakotas. And so this used to be solid across here. There was, no canyon here. This rock layer went all the way across. And my suspicion is this canyon has been cut by some catastrophe in the years after the flood. We see this in Grand Canyon, and we saw it at Mount St. Helens, and we see it here too. that you see these relatively small streams in relatively large valleys or large canyons. Even the biggest river we have in the United States, the Mississippi, even though it's a mile wide in places, it sits in a valley that's 100 miles wide. And we call those underfit streams, underfit valleys, or underfit canyons. And it means that the river flowing through them does not quite match the immense size of the valley of a canyon. My guess is 90% of the canyons and valleys around the world are underfit. And so we think that as mountains were lifted up and as erosion started to work on those mountains in the form of flash floods, in the form of mud flows, in the form of glaciation and so on, a lot of those processes could work on canyons like this and enlarge them pretty quickly.
John, it seems, at least to me, to say that all the things that carved this canyon out don't seem to be happening today. What's your take?
Yeah, and that's kind of a principle that I think is pretty true in geomorphology, is that a landscape goes through major changes catastrophically, maybe like one night at Mount St. Helens, and then the landscape just sits there until the next catastrophe. And so it's not that we don't have any catastrophes today, but I think the number of catastrophes that we have is declining from the large number of catastrophic events that we would have had as these mountains lifted up.
You've mentioned that post-flood era, that there was a tremendous amount of precipitation.
Yeah.
And so an area like this that doesn't really get a whole lot of rain.
That's right.
It was a drastically different climate at that time.
It was. Just to the north of here in Fossil Basin and Green River Basin, we've looked at, the lush landscape that was there, the amount of vegetation that had to grow there, and the water that was there. And it's much different from the climate that we have here today. I think from my perspective, as a geologist, climate change is the rule, not the exception. It's something that's been going on ever since the flood was over.
John, I think most people would look around here and say, this is a pretty bleak place. It's obviously very arid, and yet you're telling me this is a very special place.
Yeah, we're in the southwest corner of Wyoming. I spent several years up here in graduate school, and so we are standing I know it doesn't look like a lake as you look out here, but we're standing on the sediments that got laid down in a lake and now have turned into rock.
Yeah, the lake we're talking about filled up this whole basin, which is huge.
Yeah, and I can actually, from where I'm standing, I can see the edge of the basin over there. You can see these white sediments, and then those are truncated by the darker colored ridge right behind there. And the rocks in that darker colored ridge are actually sitting up like this. So that's the basin edge.
Is that then part of the evidence that you would say that this is post-flood? Because all of these are all very horizontal.
That's right. So the layers that we're looking at here, this is the early part of the Cenozoic, and that would be right at the top of the geologic column. And so we think that Cenozoic rocks in many places around the world, not everywhere, but most of these Cenozoic rocks we think are post-flood rocks. And so underneath of us, underneath of this basin, those Paleozoic and Mesozoic rocks are contorted. But these Cenozoic rocks on top, these are horizontal and flat lying, they're not contorted at all. So that means that the tectonic activity had pretty much ceased when this lake basin was filled up.
So we have this basin that it's filled with water, and we obviously then have a lot of life. When we were in the museum, we saw, I don't know how many different species of just fish and all of that. So this was a flourishing area.
Yeah, it's amazing.
With all kinds of life. Where did all of this life come from?
So it's interesting. We see things like the bats, the horses, things like the alligators, and we know the birds. All those things, they were air-breathing animals. Many of them lived a lot of their life on the land, and they would have had to be animals that were on the ark. And something happens that's different from the rocks that we see underneath. We don't see many mammals in those rocks, and all of a sudden we get to these layers, and believe it or not, Del, there are more mammal species known in the rocks of the Green River Formation than are currently living in Wyoming today.
But that sudden arisal in the fossil record of mammals should tell us something.
Yeah, the very first bats that we find, the very oldest bats that we find are right here in this Green River Formation. And yet they have fully formed wings, they look like modern bats, and where in the world did they come from? Where are the transitional forms from the animals that gave rise to bats if the evolutionary model is true? And so one of the strengths we have in the creation model is that, you know, we can explain the sudden appearance of things like bats because we think that those would have been on the ark. And they didn't get fossilized during the flood, as far as we know. When we first find the bat fossils, they're in places like this, where they have the potential to become part of the fossil record here.
John, this represents a lot of your life here. You spent a lot of time working on your dissertation here.
I did. I spent some summers here collecting fish, studying the layers. This place is like home to me.
Can you show me some of the stuff you were working with?
So we're in a commercial quarry here. It's a place where they dig these fish out and they sell them. And I think if we break some of these layers of rock open, we'll find some fish.
I'm hoping that happens.
Yeah. So what we're gonna do is go in right along a seam right in here, and you can see how this whole thing is lifting up here. Yeah, it's a big slab. And just kind of get your fingers underneath there and lift it up. And so now what we're gonna do is we're gonna take some of these chisels. Yeah, we're gonna split down through this.
Going down on it.
And see what we can find.
Is this what your research assistants did? Hold the rock while you...
That's right, all day long. Yeah, look at that, Del.
Oh yeah, look
Got
at that.
At least 3 fish here.
Yeah.
So there's one there, one right there, another one there, another one there.
Oh my goodness.
That was a good break right there.
Yeah.
So these all look like Nidia, just a little herring type fish. Boy, that one is a really nice one right there.
It is.
Del, if you look at the edge right here, you can see multiple layers in here.
Yeah, I do.
And they're not very thick. They're almost as thick as playing cards. And the conventional idea is that each pair of a layer, a dark layer and a light layer, lasted a year. But you look at fish like this guy down here, I do not see a single bone out of place. The fins are nice and splayed out right there. And based on my fish experiments, that thing sank down to the bottom of the lake and was buried in a calcium carbonate layer within a day after it laid down to the bottom. And I think that's the only way that you can explain such good preservation. And not only we see it there, but that fish, and that fish, they all have really exceptional preservation, and they have to be buried quickly.
Yeah, there's really just a lot of fine detail in that fossil there. So those small, tiny layers that we're looking at here, those are not annual layers.
I don't see any way that they could be annual layers based on how well I would think almost daily layers here. Something was different about the water chemistry here in that it was precipitating a lot of this calcium carbonate out, which was covering the fish. The other thing that's really interesting about this particular outcrop is there's several volcanic ash beds in here. And so the volcanoes are nearby, maybe some of the ones up in Yellowstone. They would erupt, and the ash would settle down through the lake, and here's this nice orange layer right here. That would be one volcanic ash bed. Here's another orange layer, not as thick. That would be another one. Here's another volcanic ash right here. And here's another ash bed that's maybe 1.5 inches thick.
Right.
These ash beds actually help us to tell time in the lake.
How's that?
If we can trace these ash beds and confidently know that they're the same from place to place in the lake basin, for example, we can look at this thickness between those 2 ash beds right there, and we know that that thickness of Green River Formation was laid down at the same time, whether we're right here in this spot or over at the edge of the lake. And it happens that we know these aren't yearly events because you can find this ash bed here, count the layers, find it at the edge of the lake, and at the edge of the lake, the thickness is more.
Huh.
And so...
Is that more layers?
More layers at the edge of the lake, and that's because you have more sediments and whatnot coming in from the edge of the lake. And so we know these aren't yearly laminations. We know
that wouldn't make sense.
The laminations are not equal from here to there. There's about 30% more layers at the edge of the lake than there is in the middle. And I don't know exactly how much time is represented between those ash beds, but one thing I do know is that the time is the same, whether it be weeks, months, or years between those ash beds. I know that there's the same amount of time. And so I was able to study the fish and the decay of the fish and the preservation of the fish during the same time in the lake's history. So I think the take-home point is that the fossil fish and the other fossils here show that these sediments were laid down rapidly. Yes, it was after the flood, but even after the flood, we have processes that produce fast layers.
You know, John, one of the things that has really impressed me is that you're not content with just sitting in an office somewhere, but you want to be out here looking at the reality to understand the truth and the facts. And I appreciate that about you, and that you understood you needed a PhD to help you do that. Is that important?
It is. At first I thought, you know, maybe why do I need a PhD? Why do I need to learn more? But the thing was that I didn't understand is how it would advance my thinking and how it would cause me to think deeper and consider other possibilities.
So would you say that for a young person who is considering one of these scientific areas, that it would be important, number one, to get their doctorate, and it's important for them to understand there's a whole lot of things to be looking at?
I think, Del, there's two things that are really important for a young scientist. And number one is to become well-trained. You need to interact not only with other creation scientists, but you need to interact with conventional scientists too. But the other thing, Del, is they need to be grounded well in Scripture. So they need to understand a biblical model, and they need to take things like this and put these kinds of things within the record. The biblical record doesn't tell us everything we want to know. It kind of gives us a framework, and we need the new generation to come up and begin to look deeper into some things. We don't know all the answers here yet. I would really like to know how much time is in between that ash bed and that ash bed. And we need some new scientists out here that are trained to think well to work on problems like that.
One of the things I noticed about these scientists was the importance of teamwork. A key member of their team is a scientist named Ray Strong. Ray is a Canadian who has developed a special set of skills working in the oil and gas industry for the last 4 decades. Although I wasn't able to travel up to Calgary myself, we sent a team to interview him in his laboratory.
My wife told me one time she felt sorry for me getting up early in the morning and having to come into work, and I said, hold on a minute. I come to work and play. This is kind of the way the field of geology is. Every single sample that you look at is different. It has a different story to tell. It has different characteristics. There's always something new. I come to work and play every day. So we need to unbox the samples and get them prepared for cutting. Basically, what we're looking at are rock samples that have been collected in the Grand Canyon, and begin doing the technical rock analysis on those samples. This involves, first of all, thin section manufacture. And so this is taking rock materials down to the thickness that you can actually see through them. And this sample is very carefully labeled with an arrow pointing up, with top, and an identifier, which in this case is, there it is, CCF1, which is Carbon Canyon Fold number 1. But initially we need to cut these rocks, dry them, and get them prepped for thin section analysis. All right, this will be noisy. Okay, right now I'm going to put an orientation mark on this rock to show what end is up. That will be crucial to determine how the bedding structure is affected by how the rock materials originally were laid down. The sample is now ready for drying in preparation for liquid epoxy impregnation in this sample. Many professional geologists aren't aware of how to do this process. There are only a handful of people, perhaps in the entire world, who know how to do this kind of thing, at least to do it well. Literally a handful of people. Okay, the epoxy is used for stabilizing the sample, and if you fill up all the pore space with epoxy, you wind up, first of all, being able to identify where the porosity is, and secondly, you stabilize all the very fine material found in the pore spaces. So this is a high-pressure cell which we use to inject the liquid epoxy into the pore spaces in the sample. In the morning, we can retrieve it. The epoxy will be solidified, and then we can handle that piece of rock safely all through the rest of the next part of the process. It is important that we continue this work and that it succeed, because I believe there's a whole side of scientific investigation that has been largely ignored. And one of the aims that I have is to chase that particular pathway and look at data that may be not necessarily mainstream, but is very, very interesting and is significant. And so that's my endeavor in working with Andrew, for example, is to see what the data says and where there's supporting evidence to make sure that that's well documented. Okay, what we're doing now is taking the epoxy away from the bottom surface, and we're exposing the rock that's been impregnated with blue dyed epoxy. And so what that does is allow us to get a nice, flat, optically planar surface. And in this case, it's extremely important. We're not mistaking scratches for fractures. So we don't want to leave scratches in the rock surface. We want to make sure that all the scratches are out so that the fractures can be easily identified. Okay, so we're going to move on to the staining process, and then it will be ready for mounting to glass. We don't want to induce any kind of fracturing into the sample, and so mounting this to glass using the cyanoacrylate glue, crazy glue, ensures that we have a good, stable surface with which to work. Imagine trying to work with a single piece of hair and trying to grind it without affecting the character of the hair. We want to make sure that we don't disturb the mineralogy of the sample as we go through the cutting and grinding processes. This slide we will now take to our grinding laps, where we'll thin it down to about 30 micron thickness. And this is kind of where the art comes into play. Do just a quick look in the microscope here, and it looks like we're pretty well at 30 microns thickness all the way across the entire thin section. We have the grains seen as being very clear. The material showing up as blue is empty space, and in cross-polarized light, if showing either as a gray or as a pale straw yellow. And that tells us that we're right on the 30 micron thickness. Back in the day when we were really busy, We would do anywhere between 80 to 100 of these types of samples a day. Personally, I've probably done in the order of about 20,000, I guess. Now we'll take the slide and look at it under the good petrographic microscope, which is a special kind of microscope made for analyzing geological thin sections. And then we move on to more elaborate testing methodologies like scanning electron microscopy. We'll take and gold coat the sample. Now, the amount of gold that we're going to put on it is very, very small, almost no value whatsoever. But it's necessary for conducting electrons along the surface of the sample in order to get the image that we want. It gives you almost a 3D visual image of the rock materials that you're looking at a very high magnification, which allows us to determine whether certain features are found in that particular rock. The electron beam runs down the column and is scanned back and forth across the sample. Okay, so we've got some very nice quartz cement showing up in here. There's some more quartz cement right there, but beautiful quartz overgrowths. Basically, the creation model provides alternatives to the explanations that are, in some cases, somewhat deficient. So looking at the creation model, for example, provided almost a stark contrast. Even though we were looking at the same data, we were quite often in disagreement over what the interpretation was to the data that we were both looking at. And I've watched this over my entire career now, as I've been involved in publishing of papers, presentations at professional conferences, and just seeing how that contrast plays out in terms of how people look at the world.
Well, there was a lot of analysis that still had to be done on those thin sections. But in the meantime, I wanted to get a better understanding of the forces that were involved that brought about those folds. And so I called my friend Steve Austin, and he suggested we go back to the Grand Canyon, but not to the bottom. But we needed to see it from the air because the forces are so large, they're so huge. You've got to get away, you've got to get higher in order to see it all.
What a great opportunity to see all this. No better way to see the country than by helicopter. In overview, it's just a tremendous way to see it. Boy, what an amazing thing this is to come over this edge. Wow, unbelievable. You know, Steve, it's really the first time I've got this sensation of all the excavation, so to speak, in the Grand Canyon. It makes me begin to imagine that it was just solid layers all the way across. Yeah, you can imagine the continuity of strata through here. When you say the continuity, you're talking about the layers that existed on this side of the canyon. They exist on the other side, but now they're gone. You're looking for the continuity between the layer here and the layer over there. And that the strata were once continuous across where the canyon is now. And we're looking at the Kaibab Plateau. It's a large part of the Colorado Plateau that has been arched. It makes an arch structure that bends the strata. We have a name for it. It's called the East Kaibab monocline. So, Steve, when we talk about the monocline, we're talking about something forcing all of that massive material up. What are the forces that are causing that to happen? Most creation geologists that I talked to suggested Pacific Ocean floor that was shoved under Western North America. The shoving of the ocean floor underneath western part of North America caused low-density buoyant material to be down there, and then at the end of the flood, it rose just because it was lighter and less dense. Than
that would push everything above it up.
It will push the plateau up higher. Yeah. Notice, here comes the arch. Okay, now look for this. Look for the strata and how they're bent.
Oh yeah, I see.
Okay, so we're looking down this flexure along the East Kaibab monocline, a line where there's been a lot of bending of the strata.
You see it all the way up there.
And the strata are horizontal, and all of a sudden they go vertical.
Yes.
Notice, it looks like soft sediment deformation. You could see the strata as they're horizontal, and all of a sudden they turn 90 degrees. Isn't that amazing?
And they're not crumbled; they're folded, you know, like soft taffy.
Now, as we come over the top of this, we're going to see Carbon Canyon down there.
Yes.
So the monocline forms this soft sediment fold structure.
And everywhere we see that monocline, we see the bending rather than the breaking. Is that correct?
It's extraordinary, but this is kind of normal Colorado Plateau monocline, okay? So the rock was not hard when it was flexed. It was soft. But there may be some other faulting in here. It may behave brittly afterwards.
If we find it where it's broken, then that would indicate those layers had already hardened.
Yeah, we're seeing the sequence of sedimentation and tectonics very closely associated in time, not separated by hundreds of millions of years. In other words, tectonics and sedimentation occur together, not separated by geologic ages.
And when you say tectonics, you're talking about the movement that
uplifts the
mountains and the plateaus and all of that. And so if the sedimentary layers are soft while that is happening, then we'll get those bends and folds.
Yes.
That makes sense to me. Well, I have to at least comment on the beauty of all of this.
Yes. Notice, again, the difference in elevation.
Yes.
We're flying below the elevation of Kaibab limestone on the north rim of Grand Canyon on the right side of us here.
But it's way below us over here.
And it's way below us on the left.
Yeah.
It drops in elevation along what? That monocline. It forms the barrier, the arch structure here. That's ultimately why we have the lake basin that was able to fill and then spill through the Kaibab upwarp, I believe, to form the Grand Canyon. I can see that the scum on the surface there, that's the tufa deposit. And that's the bathtub ring of the big lake that was filled in this basin. Can you imagine a lake in this basin up at 6,100 feet elevation, making that bathtub ring deposit?
So all of this in front of us, this was all covered with that lake.
We call it Hopi Lake.
And it comes up to a natural dam up here?
Yeah.
At this point you're talking about. And that's where at some point, for some reason, it breached. It just gave way, or maybe an earthquake or something?
Just overtopping of a natural earth dam can create spillway erosion. And there's no such thing as slow failure of a natural dam in spillover. When spillover erosion occurs on a natural dam, it erodes rapidly.
Where do you think this is occurring in terms of the flood?
I like to think of it as post-flood. The rock is already hardened. The monocline has already been flexed. The upwarp has occurred. The rocks are hardened, and then the overtopping and spillway erosion of the solid rock.
So this could be 100 years.
Hundreds of years after the flood, possibly.
How many different lakes are we talking about?
There may be 3 or 4 different lakes associated with the Grand Canyon itself. So above Lee's Ferry in the Lake Powell area, Capirates Plateau. Behind that, another lake. That could fail. And my view is the lakes failed from the top down. The spillover of this Hopi Lake over the Kaibab upwarp into the next basin below it created what? Another lake below it. And that would be Toroweep Lake. The drainage basins upstream filled first, and they spilled, destroyed their dams by spillway erosion, and they drained to the west. And you created the Grand Canyon by top-down failing of dams into lowland areas. So the erosion is channeled to form a canyon. Okay, and it's a straight canyon, but yeah, it's channelized, and that is what we see. So we see erosion in channels by spillover, it looks like. And so the lake didn't take millions of years to drain. It didn't take millions of years for the Colorado River to erode the Grand Canyon.
And you know, really, Steve, I can look around and at least imagine, envision, this wasn't carved out by a river. This is the kind of thing that you see when massive water just floods and it just evacuates all of that material.
And thinking about breach dams and the notching of the plateau by spillover, that is the latest geologic rage in thinking. The old way of thinking about Grand Canyon is, it was eroded over millions of years. No. That's becoming unpopular among geologists. In fact, as I talk to geologists, very few geologists are defending that way of thinking. They are going to something freaky and catastrophic like overtopping of lakes.
Right.
There's an ice age lake in Montana that failed through an ice dam across eastern Washington into the Columbia River Basin. A huge failure there.
So Steve, let me step back here for a second and talk about these lakes again. There's a massive amount of water represented in what we're looking at here. Is that caused from the huge amount of precipitation that was occurring as a result of the warm oceans, or is there some other source for all of that water?
Well, I like a warm ocean at the end of the flood. You could have a rainy period for hundreds of years after the flood. We could fill these basins with rainwater, and then they spill and overtop the landscape. And wouldn't that be a great place to survive after the global flood? Next to a nice big lake with lots of water and well-irrigated landscape.
Until it breached.
Until it breached, yeah. Okay, and then today it's rather arid, isn't it?
If you had lakefront property here, it all went away quickly.
Yeah, there could be palm trees. There's evidence here of camels, of geese, shorebirds on the lake. There's evidence of pike minnow. The bathtub ring right there next to where the failure point is, that's icing on the cake. That makes it real to me that the edge of the lake was up there next to the breach point. So what we see makes a strong case for some kind of catastrophic deposition of the strata of the Grand Canyon, a giant global flood, if you will. The very quick bending and upheaval of the strata forming the Kaibab Plateau, and then in the post-flood period, the spillover erosion of the plateau. In other words, we have the pieces of the puzzle that seem to assemble themselves. So we have an explanation. It's a hypothesis with extreme explanatory power. And it's consistent with the framework of the Bible.
A lot of us don't realize the amount of time and effort that it takes for a scientist, once they have done all the field work and all the lab work, to bring everything together. They now need to write it up, They need to put it in a form in which the general scientific community can look at it and review it. So we had the opportunity to go back to Cedarville and sit down with Andrew and John to discuss their findings. We talked not only about what they had found, but also about the implications of their research.
It's paper thin.
And are these all the slides that Ray sent?
He sent them to us in boxes like this, and you can see what they look like. They're just, but of course, these were hand delivered. He came down at a meeting that John was attending and hand delivered. You wouldn't trust these to the postal service.
Send them through the mail.
I can understand
then
that.
John came and delivered them to me.
So is this what you have then under the microscope?
Yep.
Yes.
How long have you been studying these?
Well, I've literally spent months, going screen by screen by screen, moving the stage backwards and forwards, systematically going through each slide, taking photos, recording details.
Hundreds and hundreds of hours under the microscope.
And I've got thousands of photographs at different points. Every time I took notes, I took a photograph so I could go back to that.
So after these months and months of looking at these thin slides, what did you find?
Well, I've put this on the screen deliberately because this is a sample that comes from right in the bend of that major fold in the Tapete sandstone. And so it's a good test case, because if there ever was going to be a sample that was going to show the mechanical or the metamorphic effects from slow, gradual heat and pressure changes and moving around, it would be this sample. So let me walk you through it. First of all, you can see that those white grains.
Yes.
Okay, the really white ones, that's the mineral quartz, which is window glass. Okay, we can see some of these spaces are still there. This is the blue, highlighting these spaces. Well, in this instance, what happened, more quartz grew, and you can see how it's joined these two grains together, and you can see that little sharp point there.
Yes.
This quartz cement, it's grown into that space. So what happens is, when it's deposited, there's water in between those sand grains, but the water has chemicals dissolved in it. And so when the water dries out, those chemicals precipitate and fill in all the spaces between the sand grains and harden it, making it a cement.
So that cement is like glue. It holds the grains together. So sand in a sandbox would be really loose, but if you put some glue in there, or what geologists call cement, that's what kind of holds the rock together and makes it hard.
What does it tell you when you see that?
Well, it's in pristine condition. It hasn't changed. This is in the hinge of that fold. You'd expect, when the folding occurred, millions of years later, supposedly, that cement should have been disrupted. It should have been crushed.
Okay.
And maybe it would have to regrow again, but you'd still see fracturing that was healed. But you don't see that in any of this. You still see the original pores.
So it tells us that the cement was added after the rocks were bent.
All right, so we were talking earlier about breaking and crumbling of a very hard rock from a larger standpoint. Now, what you're talking about is, you look at the small pieces, you also would find crumbling.
Yes.
But you don't see that.
No, that's right. You can see where grains have been compressed close to one another, and you can still see the original outlines. Here's some more cement over here that's joined that grain to this grain.
So let me ask this question then. Is that the cement formed after it was bent, not before?
That's right.
Right.
Now, you also took samples a long way away from that fold, and you wanted to look at those and compare those to the fold. We haven't seen one of those. Do you have
I've got
a
one
slide
right
of that?
here. Okay, one right here. And it has exactly the same features. Now, we're going to have to adjust this again. Let's get it back into focus, because we can move it around. Okay, you can see there, again, you've got the same. You've got the blue spaces, you've got, look at all the different size grains of the white ones of quartz, you've got feldspar, you've even got some rock fragments there. So, it doesn't look any different.
So let me put you on the spot here, Andrew. If I were to mix up a slide from the fold and a slide, how far away? Was it
this one here, that was above Little Colorado River. So as the crow flies 5 to 6 miles.
Okay, so if I were to switch those up and put them under the microscope and say, Andrew, is this from the fold or is this from 5 miles away? Could you tell?
I couldn't tell because there's no radical difference.
That tells you
They're
something.
essentially the same. And that was the whole point of taking those samples to be a control.
The fact that we find them the same, every sample of the sandstone has exactly the same features, is quite telling. It means they folded before they hardened.
Well, let's go back to the conventional paradigm that would say that the folding took place as a result of a metamorphosis in the rocks. What would this look like if that had occurred? Would it look different, and why?
There would be a whole set of different features that are not present here.
Yeah, metamorphic rocks under the microscope look distinctly different from this. Here's a slide that might even look closer. When you take a sandstone, which is the type of rock that we found in that fold, and you put a sandstone under metamorphic heat and pressure, it's going to look something like this. This rock is called a quartzite. The dominant mineral here is going to be quartz. And one of the things you notice right away is that there's not any blue in there.
Right.
And that means that all the cement has grown in between the grains. You can still see some of the grains in there. I think, Andrew, if you put it under cross-polarized light, the grains show up even better.
Here's where we look at under cross-polars.
But you can see how these grains interlock with one another, just like pieces in a jigsaw puzzle.
This is the puzzle you were talking about.
That's right.
And here's the
turn the
puzzle
light
put
up
together.
a little bit more, and you see how
very
you've got
different.
Lots of these connecting points, these junction points that are often, 3 grains at what we call a triple point.
So, Del, we think if the conventional paradigm were true, that the rock samples we took out of that fold would look more like this than the sample of sandstone that we looked at.
Well, to an untrained eye, I can tell you this, it is a radically different picture than what we saw. So it makes one think the current paradigm is not correct. Is that what you're assuming here?
You can see why it was important to make the thin sections and to look at, because you can't see these effects in a hand specimen. You've got to really dive into these grains at this microscopic level, and all geologists do this. It's part of the detective work. You have your framework of thinking and you say to yourself, well, if I go and get samples, what do I expect to find? And you set up some questions to answer and what you expect to find, and then you go out and you do the tests to check whether, and if you don't find what you already predicted you're going to find, you're going to have to change your model. Try and change your model for how you understand these rocks.
So what are you now waiting on from Ray?
Well, Ray is also going to talk to us about the results he got from using a scanning electron microscope, which is going in an even higher power of magnification. This is just in 2 dimensions. He's able to look in 3 dimensions. You'll be able to see the quartz cement, the way it's grown between the quartz grains. And that'll tell us whether there's been any mechanical disruption or whether the cement has occurred as the last stage in the whole process.
Okay.
There we go. Oh, hello, Ray. It's so good to see you again. And unfortunately, we got to do this by Zoom. And I have in my lab today, Del Tackett is with us.
Hey, Ray.
And, Andrew Snelling is with us.
Good to see you again, Ray. It's hard to believe. It's nearly 2 years since I was up there last with you in the lab.
I know. I was just looking at some of the images that we were doing while you were up here, and looking at the dates on them, and it's hard to believe.
So, Ray, we want to look at one of the thin sections from the tight fold in Carbon Canyon. And here's the thin section. And one of the things that struck me right away when looking at these thin sections was the amount of porosity in these rocks. Even at this place where the bend was really tight, there's still a lot of empty space in there. And Ray, could we look at an image from this very same rock sample, sample number 10, and let us know your observations about what you see with the scanning electron microscope.
So here we have an example of a scanning electron microscopy image. If you can see my cursor here, that's a sand grain right there. And associated with that sand grain are a number of overgrowths of quartz.
Ray, when you say overgrowth, what do you mean by that?
Okay, this is actually the cement. The important thing to look at here is that the individual overgrowths that you see here have not been disturbed. Their contacts have not been disturbed by any kind of mechanical deformation.
So we're actually seeing that the cement hasn't been damaged because you've got these pristine ends of the crystals as they've grown on the original sand grains.
So that shows that the bending took place and then the rock became a solid.
Exactly. And of course, this is at a much higher magnification, so any even subtle deformation would show up between these cemented particles.
So Ray, that sample was, as you know, from the Carbon Canyon Fold in the hinge, and that was in the tapetes. It's probably going to be helpful now if we look at a regional sample. So that's TSS3. We might want to just look at that too, because that's a long way away from these folds.
So there's an awful lot to see in this particular image, but the overgrowths are basically two types. We have beautiful quartz overgrowths, but you've also got precipitation of clays, which lends to, I guess, what you'd call the dirty appearance of this particular rock. The overgrowths that you see here are quite pristine, indicating that they've been growing into open pore space. I don't see anything unusual here. These rocks haven't been dislocated, haven't been fractured, all those sorts of things.
So I asked us earlier of Andrew, if we were to put several of these pictures, if I were to mix them up, would you be able to tell me, you know, which belongs in the hinge and which does not?
No, I couldn't.
And it seems to me that that is, from my perspective, kind of the summary of this, is it, and what you wanted to see in the very beginning.
Well, the sequence is sedimentation, folding, then hardening.
That's correct. Now, you can help me here because it seems to me, from a very amateur perspective at this point, that we're looking at a very significant finding. Anything that begins to show that a theory is wrong is a major observation. And I'm almost getting a little deja vu here back when we were looking at the soft dinosaur tissue. We were looking at something that from the conventional paradigm's perspective should not be here, right? The soft dinosaur tissue should not be here because it is millions and millions of years old.
There's no mechanism to preserve it for millions of years.
Correct. And now we're looking at a microscopic level of the grains and the cementation and all of these things that we've been looking at. And we're seeing from a conventional paradigm perspective what shouldn't be there. That to me is fascinating. Yeah. And I'm excited to be here to share that with you.
And it kind of blows the mind to think that we're looking here we've looked here at the microscopic level, but it gives us a narrative to explain, you know, the building of mountains. So it's quite dramatic because, as you say, you know, just these observations under the microscope help us to put the pieces of the puzzle together in the chronology and when these mountains formed. It wasn't hundreds of millions of years after the layers were deposited. It was only months after the layers were deposited. And that's a radical departure from conventional explanations of the building of mountains.
I'm reminded of a trip that was organized for the heads of our international oil and gas company. Part of that was a helicopter trip over Jasper, Alberta. Well, there are massive, massive folds in the Rocky Mountains. And one of the individuals who happened to be an engineer, long time standing with this particular company, he later recounted to me, he said, I saw all these folds in the rock. I can't even imagine how you could think that those would have been formed in solid cemented rocks. They had to have been soft when those big folds were formed. So it's critical to state that we're looking at scientific evidence. We're not imagining this stuff. We're actually looking at scientific evidence that supports a particular model, one of a young Earth and short events that made the features that we observe.
Ray makes an important point. There really is a lot of evidence that supports the creation model. But we've only been able to show you a brief summary of just one research project. Even in this documentary, there were many conversations we had to leave out, details we couldn't include, scientific evidence that took too long to explain. But my hope is that you have a new appreciation for how creation science actually works. I also hope this film reminds you that Genesis is the best explanation for everything we see in the world around us. I was fortunate enough to meet up with Andrew one more time at my home in Colorado, where I spend every day under the shadow of an enormous mountain.
So Andrew, looking back at all that we've talked about and all that we've looked at, you're still in the process of this whole research, right? How many papers have you already published?
2 have already been published. A third is in the process of being published, and there's four more to come. And so those papers are long and detailed with all the microscope photographs and all the descriptions of the rocks, because it's reporting all the observational data that anyone can go and look at and read.
I guess the question is, how is the world going to respond to that?
So if they were to admit that my evidence indicates there was a catastrophic global flood with a short period of time of catastrophic processes, a humongous amount of energy and earth movements to raise up these mountains, they're going to have to forget their millions of years. So they're going to have to reject their own interpretive framework. So they're either going to ignore the research, which is what they commonly do, or attack the scientists.
And yet you still go on. You still proceed in this work.
Absolutely, because it's part of our worship. As we've been given dominion over the earth by God, we've been given brains to use. He expects us to use them. It's an act of worship to Him. And of course, we've got a lot more work to do. I mean, what about the animals? What were they doing at this time? What about the people that were descended from Noah? There's lots of questions that we have yet to answer, to link from the time that Noah got off the ark with the rise of the mountains into the civilizations that everyone is familiar with. So we've got a lot of work ahead of us to get a fully integrated package of explaining the world around us as it is today.
So that brings me back again to some things that we've talked about before. We talked about them earlier in the previous film, and that is the whole notion of creation scientists and the processes that a creation scientist goes through, and that has all been exampled for us in this project.
Well, anyone can collect rock samples, anyone can do laboratory analyses, but they're just numbers, they're just observations of minerals. You've got to be able to put that within an interpretive framework. And I start with the interpretive framework that Genesis is literal history, that God has given us that written account of history, and it describes the Genesis flood. And so then I start to look at the data, the observational data within that framework. And so that's what creation scientists do. We ask questions and then we do the research to see if we can answer those questions, but all within the interpretive framework of Genesis.
Andrew, there are still a lot of questions that are left unanswered. Where do you see creation science going from this point forward?
Well, actually, I'm quite excited because we see another generation being raised up for which we can hand on the torch. And you know, my research and others who are doing research like this are setting examples for the younger generation. We want to equip them and challenge them with the things that have yet to be answered, to take up the questions and run with it and do the necessary research. So I'm quite excited about what God can do with young people in the years ahead.
I'm Del Tackett. I'm with my friend Thomas Purifoy, and I'm excited to tell you that we have begun what we're calling the Genesis Fund, the ability to try and fund some of the research that we saw all the time during the Genesis film.
Lots of it.
Is desperately needed. What are we going to do with this fund?
So we've partnered with a 501c3 that has set up this fund where the money will be used to basically support creation science and enable a rising generation of young scientists to be able to pursue their education and their dreams and their scientific endeavors.
Creation science is not funded. It's not funded publicly. The only way it's going to be funded is privately. And that's what we're hoping will happen. We're hoping that you would find yourself wanting to support this kind of work.
So if this sounds like something you'd like to be a part of, please help support us, and more important, help support creation science.
The exciting thing about this, to me, is that we will also be encouraging young people to move into these areas, to be a creation scientist themselves. So I'm excited about this, excited about the possibility of not only funding these, but giving you an opportunity to film and let people see how that process works.
You know, this is really a fascinating process. Just a small handful of folks, and we would meet a scientist out in the field, and then we would spend hours together. And in that process of interviewing them and walking from one location to the other and looking at all of this amazing stuff, I think I learned more than anybody will ever learn just by looking at the film, because there was so much material. And that's why we're doing Beyond Genesis History, and in Volume 1 to look at the rocks and the fossils. The data that we're looking at is the data that matches exactly what the history that God has given to us about why all of this occurred and how it occurred. It's not just enough, I think, to give people a survey. It's really important for people to understand more of the details, to have a deeper foundation of the fundamental truth of what that evidence is showing.